everyone, my name is Miss Garcia and I'm the 4th grade writing and science teacher over at Luna Primary. Hoot hoot, go Owls. If you are joining me for the first time, it is really nice to meet you. I'm so happy to have you here with me. And if you are joining me from my homeroom, my classroom, hey guys, I'm happy to have y'all here as well. So I'm just going to go ahead and jump right into it. We are going to be investigating forces this week. But before we begin, I'd like to ask you a question. What happens when you rub your hands together back and forth really quickly? If you answered that they heat up or they get warm, you're correct. Okay, if you don't believe me, let's try it together. First thing I want you to do is, with clean hands, go ahead and touch kind of like the bottom of your face and just get a feel for how hot or cold your hands are. Now rub them together really quickly. Stop. Go ahead and touch your face again. And you should notice that your hands feel a little bit warmer. Now, obviously, the longer you rub your hands together, the warmer they will get. And we didn't do it for that long, but that is an example of what we call friction. Friction slows things down and is evident when tires move against pavement, shorts slide along the playground slide, or even socks skid on a clean floor. Can you think of more examples of friction in your daily life? Go ahead and put some examples for you to see if you couldn't think of any. Before I go any further, I want to go ahead and go over this week's vocabulary and make sure you are familiar with it and actually understand all these words that we're going to be using, because you will be hearing them a lot. So here we go. All right, our first vocabulary word is the word force. And force is a push or pull that causes an object to move, stop, or change direction. Force. Right here we have a roller coaster in here, and that's their picture example. Why do you guys think they used the roller coaster as an example of the word force? Okay, good. There's a lot of pushing and pulling involved in roller coasters. If you've ever ridden one, you know that, okay? It is made to push and pull you and change the direction you're going in. There's some that go forwards and then backwards, some that go in loops, some that launch really forward really hard, some that start slowly and build up lots and lots of momentum and then go really fast. But roller coasters are great examples of force because there's a lot of pushing and pulling going on there that is causing moving, stopping, and change of direction. The next word is push, and to push something means to use force to cause something to move away. So in our picture example, we see what looks like a brother and sister, and it looks like the brother is pushing his sister in the wheelbarrow. I've always wanted to do that. If you've done that, I'm kind of jealous. All right, third word is the word pull. And to pull means to use force to cause something to move closer. So this is an example that's giving me a little bit of anxiety to look at, but it looks like somebody is rock climbing up a pretty steep cliff, and their friend is reaching out to hopefully pull them up to safety. Our next word is gravity. And gravity is a force that causes objects with mass to attract each other. In our picture example, we have an example of a coffee cup that looks like it has been dropped, and we see gravity is pulling it to the floor, and we all know what's going to happen once it hits the floor. Friction. Friction is a force that slows or stops motion when objects rub together. So we just created or demonstrated an example of friction by rubbing our hands together. Our next word is magnetism, and magnetism is the force produced by a magnet. In our picture example, we have one big magnet and lots of screws, paper clips, looks like some needles even, are attracted to this magnet. Our next word is position, and position is where an object is located. This looks like Finding Nemo, and this is just an example of his position, kind of semi-hidden, not hidden, down deep somewhere in the ocean. Our next word is movement, and movement is a change in position or location. Pretty obvious animal example here. If you recognize the animal, you know that they are known for moving fast. And that wraps up our vocabulary, so we can go ahead and actually jump into the lesson now. So our focus questions for this week are, what are some forces that can affect objects? What are some ways in which forces affect objects? Most of you guys should have had at least a little bit of experience with forces of push, pull, gravity, and magnetism back in second grade. You may have observed and identified how magnets were used in everyday life. You may have traced the changes in the position of an object over time, just like a cup may be rolling on the floor or a car rolling down a ramp. And then in third grade, you may have demonstrated and observed how position and motion change by pushing and pulling objects like swings, balls, pulleys, and wagons, which all demonstrate work being done. Something else you may have done is observed forces such as magnetism and gravity acting on objects. Now that you're in fourth grade, you're going to be designing a descriptive investigation to explore the effect of force on an object. If that sounds really crazy and fancy to you, I promise it's not, and I will be walking you through how you're going to be doing this at the end of the video, okay? If everything that I just said made absolutely no sense to you because maybe for whatever reason you did not learn very much about force of motion back in second and third grade, guess what? It's okay. That's why you're here today, and you should be leaving this video with lots of new knowledge that you can actually use in everyday life, okay? So the main piece of literature for today's lesson is going to be this Investigating Forces STEMscopedia article. This is going to be where the meat of our lesson is today. If you would like to save a copy for yourself and read this on your own time, maybe after the lesson, I've included the link. Hopefully it's in the description box below for you to open this up on your own, or you can always just kind of pause the video, read on your own, and then resume as you are ready. A mother hears a loud crash in the living room. She walks into the room to see her 7-year-old son looking at a broken vase on the floor. "How did that happen?" she asks. "I don't know. The vase just fell all by itself," the boy says. The mother says, "It couldn't have moved by itself. Didn't you learn in school that nothing moves without a push or a pull?" Is what the boy says possible, or is his mother correct? In this lesson, you will answer these and other questions about how pushes and pulls change motion. What are some forces that can affect objects? A force is a push or a pull. There are several kinds of forces. Some forces are hard to notice. Other forces put on quite a show and are easy to notice. Some forces need to touch the thing they act on. Other forces can change a thing without touching it. When someone pushes or pulls on something, it is easy to see the effect. You push on a bicycle pedal and the bicycle moves forward. A dentist pulls on a tooth and the tooth comes out of the patient's mouth. Other forces may seem more mysterious. So before we move on, pushing and pulling are both examples of forces. Can you guys think of any examples of pushing in your day-to-day life? Hopefully not pushing your brothers and sisters, but other examples of pushing. Go ahead and shout them out. Awesome. What about pulling? Can you guys think of any examples of pulling in everyday life? Great job. So for example, a magnet can both push and pull on another magnet. A magnet can also pull on something made of iron. This happens because of invisible lines of force surrounding the magnet. Sound impossible? Remember that even if we can't see the force like in a magnet, it's still there. Gravity is another force that may seem difficult to figure out. Gravity is a force that pulls all things with mass toward all other things with mass. However, gravity is a very weak force unless one of the objects is very big, such as planet Earth. Things fall to Earth because the force of gravity pulls on them. Gravity also holds things on Earth's surface. If it weren't for gravity, things would just float away into space. Gravity is always a pull, never a push. So we're going to take a look right here at this picture. So if you see, this is a magnet right here, and all these lines around it are those invisible lines of force that surround the magnet. Now, we don't see those in our everyday life when we're working with magnet because, like the article said, they're invisible. But if you're wondering how magnets are able to attract other magnets or metals, it's because of those lines of force, okay? So you can use bits of iron to see the field lines that surround a magnet. And that's what this is in this picture. So nobody drew this. This is actually bits of iron, like tiny, tiny, even tinier than sand, pieces of iron that they used to show all those different field lines or lines of force that surround the magnet. If you need a reminder on what mass is the amount of matter or stuff in something. So that is what the article is referring to over here when it says gravity is a force that pulls all things with mass. So all things that contain matter or something. Okay. Friction is a force that slows moving things down. Friction acts in the direction opposite to motion. Friction can also keep things from sliding around. The materials involved help make this happen. The force of friction is greater when a surface is rougher. You can walk up a steep sidewalk because friction keeps your shoes from slipping. You might not be able to walk up the same sidewalk if it were covered with ice. The force of friction would be much less strong between your shoes and the smooth ice. So let's think a little bit deeper into this. Yes, we know that friction is what's helping you be able to walk up the sidewalk that's steep without falling down, but what elements of the sidewalk also kind of help? What's the difference between a sidewalk on a normal sunny day and a sidewalk covered in ice? So when the sidewalk is dry and it has that gritty texture kind of slows your feet down as you go, and it makes it so that you don't slip or slide down as you're trying to walk up this steep sidewalk. That friction is missing when the sidewalk is covered in ice because now the sidewalk is nice and smooth and there's nothing there to grab your feet as you're walking and kind of slow you down. Not that the sidewalk literally like goes up and grabs your feet, but the texture is what's kind of going against your feet to make it go slower. Are there any elements that your shoes may have that create friction? If you're not sure, maybe go grab the bottom of a tennis shoe or something right now and just turn it upside down. Tell me what the bottom looks like. Okay, I'm hearing a lot of different things. Some people's have ridges. Some people maybe have picked up a cleat. There's little spikes sticking out. But basically the main thing that the bottom of everybody's shoe should have in common is that there is some kind of texture on the bottom of your shoe. There may be a pattern. There may be even a just special way that the bottom of the shoe is built, just depending on what kind of shoe you picked up. The point is the texture at the bottom of your shoe helps create friction as well, so that you don't slip. If you have like a pair of slippers or maybe even like slipper boots, I have a pair of slipper boots that sometimes I do wear out because they look like normal shoes. But I've learned my lesson. Those slippers have no kind of friction at the bottom. Last little example of this is those of y'all that play sports. If any of y'all play an outdoor sport that requires cleats or even an indoor kind of turf sport that requires cleats, why do you need cleats? What's the purpose of them? Good. Okay. Those cleats are made so that you are able to have a better stance and kind of foot on the ground when you're playing whatever sport it is that you are playing. Okay. I know sometimes even the type of cleat varies by sport because each sport is different and the functions of how you need to be able to run or walk or move your body are different. So those cleats help to create enough friction between you and the ground so that you can actually have a strong stance and not be moved quickly or just knocked over or even just slip really easily when running down the field. All right, let's keep going. A car is parked on a steep street. The car is not moving. When something is not moving, we know the forces are balanced. This means they cancel each other out. Which force is pulling the car down the hill? Which force is balancing this force and keeping the car from sliding? We just talked about both of these forces above, okay? So if that car did not have brakes, what force would be pulling it down the hill? You answered gravity, you were correct, okay? Which force is balancing the force and keeping the car from sliding? So gravity naturally wants to pull that car down the hill, but something's stopping it. What's creating friction? The push of the brake is creating friction, okay? So what are some ways in which forces affect objects? Even pushes and pulls are not totally simple. For example, forces always come in pairs. If you push on a large tree, nothing happens. If you try to pull the tree out of the ground, nothing happens. When you push the tree, another force is balancing your push. When you pull the tree, another force is balancing your pull. But where are these other forces coming from? When you push on a tree, the tree pushes back with an equal force. The result is that the forces are balanced and nothing moves. Similarly, when you pull on that big tree, the tree pulls back. This happens for all forces. When the force of Earth's gravity pulls you to the ground pushes up with a force equal to your weight. A really cool recent example of forces being balanced. I don't know if y'all saw the trend going around for a few days about brooms being able to stand up. If you heard that it was because the earth was tilted a certain way that day or whatever, that's not true. According to a few knowledgeable people that I talked to, your broom can stand up if you balance it correctly pretty much any time of the year. But that's a great example of the forces being balanced out, okay? Normally gravity pulls your broom down just because of the design of it and how it's made and the shape of it and all that. But if you sit there and you mess with it and you balance it enough to where the weight's distributed evenly, then it stands up straight. And that's a great example of forces being balanced, okay? And then as soon as it falls over, those forces are not balanced anymore and gravity is pulling it down, okay? Right, here's another example in this picture of what looks like two people pushing on a wall. The caption says the wall pushes back on the people, so the forces on the wall are balanced, okay? So no, the wall is not like growing arms and pushing back, but the wall is built to withstand falling down. So it's built to where if anything were to ever push it down, anything bigger than humans, maybe like wind, other buildings, stuff like that, hopefully it would be able to withstand whatever is pushing on it, okay? So they should have pushes back right here, kind of in like quotation marks, because it's not technically pushing back in the way that y'all think, but the forces are balanced, so nothing's happening to it. In this picture, we have a waterfall and somebody standing at the bottom of the waterfall, and it says, because of the force of gravity, the water speeds up as it falls. Forces are not always balanced, however. When forces are unbalanced, something must change. These are the changes that can result from unbalanced forces. Something speeds up, that's what we were just talking about. Something slows down. Something changes the direction of its motion, or something changes shape. We're going to see an example, a small example of that in a minute. So, what do you think? These changes happen only while the force is acting. Also, while the force is acting, the change keeps increasing. For example, something will keep going faster if a force keeps acting on it. When a rock is falling, the force of gravity is acting on it. Because this force is always acting on the rock goes faster and faster until it hits the ground. That's one of the changes they were just talking about up here, okay? Another example is when you throw a ball, it speeds up until it leaves your hand. At that point, the force of your hand has no more effect on the ball, and the ball slows down. The ball slows down because the force of friction between the air and the ball acts in the opposite direction of its motion. So you may not have realized that force is necessary to make something change direction. So they have a couple of examples right here if you want to read through this on your own time. All through right here and all through right here. This is an example you can do kind of at home with somebody else. Kind of hard to do by yourself. And then obviously you need these items for this example. But we're going to go ahead and watch a video on a different example.
We've been working on this model roller coaster, trying to get this marble through both loops. But it keeps running out of energy before it gets through the first loop. It seems like the marble doesn't have enough momentum to carry it through the coaster. I'm sure we'll find a solution in no time. Every day we're surrounded by examples of forces in motion. Forces can cause an object to move, like the pull of a paddle propelling a kayak through the water. Forces can cause an object to slow down, like air pushing against a parachute as a skydiver lands. Forces can cause an object to change direction, like a soccer player's foot intercepting a pass and sending it back down the field.
Hey, I think I'm beginning to understand the problem with our roller coaster. The marble needs more energy to get through the loop. I just need to figure out what changes need to be made.
Right. We need to increase the force, causing the marble to move forward. We also need to consider friction, which might cause the marble to slow down.
What do you think we could try or investigate to make this model roller coaster work? See if you can come up with some answers.
Give you some time. So what could we change to make the marble complete the roller coaster? Nice. Those are all great ideas.
We thought of a few experiments that might tell us what changes could be helpful. I hope you thought of some ideas too.
Okay, let's think about how to set up the experiment.
One of the experiments will test whether the height of the hills will change how far the marble will travel. I'm going to use a ramp and a toy car.
Since we're testing the effect of the height, let's keep everything else the same, so we'll be able to see the change we observe in the distance.
Here's a data table showing 4 different ramp heights, with 2 trials at each height to increase our accuracy.
We can measure the distance traveled with this meter stick and see what our data tells us. And we can use these books to change the height of the ramp. Here we go.
So how many centimeters was it?
41 centimeters.
Let's try it again for accuracy.
Looks accurate, 40 centimeters. Now let's add a book to increase our height. "64 centimeters.
Here are the rest of the results from our experiment. I already know that gravity pulls the car down the ramp, and from our results, it looks like the taller ramp makes the car travel further.
I think this might be helpful for our marble roller coaster.
Another experiment we could try is seeing if we start the car at different points, if that will make a difference. We could use the ramp to test this experiment.
Great idea. We'll need to use the meter stick to mark some different distances on the ramp and to measure the distance the toy car travels each time. The ramp can stay at a constant height, and we can change the starting point of the car to see what effect that has on the distance. Let's try it.
Here are the results. It seems like when the car starts further up the ramp, the object travels farther.
So in our marble roller coaster, let's try moving the starting line backwards to see if that will help the marble make it through the first loop.
There are so many things we can try. I could do an experiment to test the effects of friction on the car's motion.
We could also test whether a greater force applied at the launch would increase the distance traveled.
I think I'll start by changing the height of the first hill and see if that helps. I can always do other experiments later.
There are so many ways that forces can affect motion. Maybe you can come up with your own experiments.
For now, wish us luck. See you next time.
So based off of their experiments they performed, do you think the change that she's going to make to their model is actually going to go ahead and get that marble around the loop? I think it is as well. We know from what we just read and from what we just saw that when you start from a higher point, the higher up you go, the faster it's going to end up going, and that's probably going to give it enough momentum to be able to go ahead and go up and around the loop and keep going and complete the model. So you may think that if an object is motionless, no forces are acting on it. But remember, that just means the forces are balanced, okay? If an object is staying still, those forces are balanced. In fact, forces act on everything on Earth. Even when you are sitting still on the ground, gravity is pulling you toward Earth. Earth's force pushing against you balances the force of gravity. You are motionless because these forces balance each other. It is easy to ignore the force of gravity unless we're falling, but it is always present and always the same. So if you want to dive even deeper into it, they have a scale activity right here. And I'm going to go ahead and read through it for you, okay? So the force of your body pushing down on Earth's surface is called your weight. In America, weight is usually measured in pounds on a scale. Many scales measure weight by pushing or pulling on springs. The spring moves a pointer up or down. The number the pointer points to is the object's weight. You may have a bathroom scale that measures weight by compressing or pushing a spring. It is easier to understand spring scales. It is easier to understand spring scales by studying a simpler scale that stretches or pulls on a spring. You can see these scales at most grocery stores. There's usually one hanging near the fruits and vegetables. Try weighing different things on a spring scale. Notice that when you double the weight, the spring stretches twice as far. 2 apples should weigh about twice as much as 1. A quart of milk should weigh about twice as much as a pint. Which force are you noting that causes these changes? So hopefully you are very familiar with what all of these terms mean now, and we're going to play a quick game, okay? And we're going to match the names of these forces to their descriptions. Y'all are going to help me draw a line from each force to the correct description. First one, gravity. All right. Okay, next one, spring force. Good. Okay, friction. Good, slows down moving objects. And lastly, magnetic force. Good, pulls on iron objects. So I am going to leave you with a little bit of homework today. If you have received your science packet in the mail, that's where I am getting this from, okay? And you go to page 21, you'll see this experimenting with forces activity. And I noticed that it jumps right into the instructions and doesn't really give you much guidance on what materials you're using. So I'm going to go ahead and give you a list of materials you can use. And they're just your common household items. So like cereal boxes, you may need a calculator for calculating the average during the activity. Wind-up toys, magnets, paper clips, toy cars, some different surface options to change up the texture of your surfaces would be like foil, cardboard, carpet, bubble wrap. Other items you're going to need are rulers, marbles, different balls like golf balls, ping pong balls, tennis balls, your own makeshift ramp, paper, and spring scales, okay? So these are some suggestions for materials you can use to complete this activity if you were maybe a little bit confused. And the activity is on pages 21 and 22 of the packet. Pages 16 through 20 contain our questions. We are going to be going through these on Thursday. If you feel confident answering them, you may go ahead and do them. If you're reading through them and you're still a little bit confused, just go ahead and wait until Thursday and we'll go through them together. So thank y'all so much for joining me today. I hope you guys enjoyed our lesson. I hope you are taking something from this, and I will see y'all Thursday. Bye.